1. This is the presentation of proof, the continuation of last presentation, that is about atom. This is the second part where I am going to cover Rutherford model and Bohr atom model and some of the hydrogen spectral lines also covered in this one. In additional, some of the important problems which was asked in the previous year question paper pattern that also discussed here, where I have mentioned on the presentation on any side of the corner, you just go through. If you are having any doubt, you just pass your comment on the comment section so that I just try to explain. The first problem of this session is about a Bohr atom model. In Bohr atom model, the electron which is replaced by the another electron which is having a mass of 150 times greater than this one, and which is having the same charge, and the radius of the first electron here is A0. Then the new atom will be, what is the radius of the new atom? See, only changes here is A0 for the first electron which is having 150 times less than the second one mass, and radius here is A0. For the 150 times greater mass, what is that radius? See, for this one, let me show you here for how you can find out according to the Bohr atom model. Radius of the orbit here is, see, Rn is equal to n square h square epsilon naught divided by pi m e square z. Remember this one. Based on this, R is directly proportional to number of the orbit and atomic number, and you can use find the velocity also here and the time period of revolution. See, based on this formula, you just remember here. Now let me tell you, in this case I just write on the formula one more time. See here, R is equal to, I just mentioned here for the first orbit. See here, n is equal to 1, so R and number of orbit here is, according to this one you can change here, epsilon naught h square n square divided by pi m e square z. Okay, now see, from this one, R is mainly proportional to, I just mentioned here, R is mainly proportional to 1 divided by m. Only mass has been going to change. Again, I just mentioned here from this one, R1, that is for the first electron radius, R1 by R2 is proportional to, that is 1 divided by m1 and 1 divided by m2. See, from this one, what you are going to have here is, I just mentioned here, r1 divided by r2 will be equal to m2 divided by m1 here. Now, already they have mentioned r1 here is a0 divided by r2 will be equal to m2 here is 150 times of m, and here is m and m will be cancelled here. From this one, r2 will be equal to a0 divided by 150. So answer in this case. Okay, now the next important problem here is the wave number of energy emitted when an electron jumps from fourth orbit to the second orbit. See here, in this case, let me show you here. If the electron is jumps from the fourth orbit to the second orbit in a nitrogen atom. See, this is about the hydrogen atom. When the electron is moving from fourth to the second orbit, that what they have given here is about wave number here is 20497, that is 20,497 per centimeter. Now for this one, let me tell you, in this case, the wave number of energy of the same transition for the helium atom. See here, what are the changes here is for hydrogen atom, if it is moving from 4 to 2. So what you have given here is wave number, this is the value. The same one, same transition from 4 to 2. But in case of helium, so helium is only going to change. What about the wave number? See, wave number in this case, it's one of the unit of frequency, right? Unit of frequency, it's mainly used in atomic structures and even molecules, even some nuclear spectroscopy also it has been used. And mainly it is equal to the true frequencies to the ratio of true frequencies to the speed of the wave. See, for we can understand this one, let me tell you here. Already we know this one, E equal to h nu. From this one, nu is equal to c divided by lambda, where c is about the speed of the light. Similar concept here, nu divided by c. See, that's what they have given. What it mean that frequency divided by its speed of the wave. That one, what we can mention here is 1 by lambda. That one we call it as wave number. See, hope you understand from this one. See, from this one, wave number I just mentioned here, v dash is equal to 1 divided by lambda. Already we know this one, the formula here is r z square. That one we are keep on seeing this one.
1 divided by n1 square minus 1 divided by n2 square. See, in both the cases, what they have mentioned here is both are moving from fourth orbit to the second orbit, so that in both the case this one will be the same. The only variation, even are also same, only variation here is wave number. Say this one wave number and to the atomic number, because hydrogen atomic number is different to the helium atomic number. So from this one, v dash is proportional to z square. Similar concept I just mentioned here. V1 divided by V2, that is wave number for the hydrogen to the helium, will be equal to Z1 square divided by Z2 square. So therefore, what I'm going to mention here is V1 already they are given 20,497 divided by for V2. V2 here is for helium they are asking here. That one will be equal to for hydrogen atom atomic number here is 1 square divided by helium here is 2 square. Now I just mentioned here. So what we are going to find out here is V2 is equal to 20497 into 4. So what you are going to have in this case, so here is you just multiply this one. So what you are going to have here is 81988 per centimeter. So that one, see, I just mentioned here per centimeter. So that answer in this case here is this one. Here is the wavelength of first member of Balmer series of hydrogen spectrum. See, first member of Balmer series of hydrogen spectrum wavelength they have given, that is 6564 angstrom. And the wavelength of second member of Balmer series. See, for this one, wavelength of second member. See, for this one, I hope you know about the formula. Let me tell you here. In this case, 1 by lambda is equal to this one. See, 1 by lambda is equal to that one will be equal to r square z will come. See, from this one, this is mainly proportional to the number of series here. See, this one from here I just mentioned here, 1 divided by n1 square minus 1 divided by n2 square. See, from this one, lambda is proportional to this one. See, from here what I'm going to mention here is lambda 1 divided by lambda 2 will be equal to lambda 1, that is the transitions between 1 and 2 here. So I just mentioned here in this case 1 divided by, just mentioned here, 1 divided by 1 to 2 square minus 1 to 1 divided by 3 square here, and whole divided by, in this case this is lambda 1 and lambda 2 here is, again I just mentioned here, for the second member here is 1 divided by 2 square and 1 divided by 4 square. See, in this case, hope you remember this one. This is the first orbit and the second, third and fourth orbit here. See, if it is moving from third to, see, this is third to 1, or even next one is fourth to 1, that is about the second member here. I just mentioned here 4 to 1. So according to this, I just mentioned here lambda 1 divided by lambda 2 will be equal to, now I just substitute the values here. So this will come in numerator, this will come in denominator. So I just mentioned here 1 divided by 2 square minus 1 divided by 4 square whole divided by, now this one here is 1 divided by 2 square minus 1 divided by 3 square here. Now you just mention here, this is a 1 divided by 4 minus 1 divided by 16 here, and this one from here, this is 1 by 4 minus 1 by 9. Now you just simplify here. From this one, lambda 1 value they have given, that is 6564, and divided by lambda 2 is here, and this one I just simplify. What I'm going to get here is this one, this will be around 1 divided by, yeah, see, common, you just take this one, you just simplify here. This is a common thing I just mentioned, simply 16, no, not 16, this one is around 20 here, and you just simplify this, and this one here is 1 by 27. So what you are going to have here is 27 divided by this, 27 divided by 20 here. So for see, in this case you just use shortcut methods. See, shortcut method I just mentioned here, approximation you just mentioned this one like this. This is approximation. So according to this, what I'm going to mention here is this one here is 3 by 2. So from this one, lambda 2 is equal to, lambda 2 is equal to 6564 into 2 divided by 3. You just cancel it and multiply to this one. This will be approximately 4000, 4200 will come approximately. So in this case, what you're going to have the answer here is
The next problem here is which one of the following transition in an hydrogen atom emits a photon of a higher frequency. See here, these are all the transactions from 226, 622, 221 and 122. In this case, which is having higher frequency. See, according to this one, let me tell you in this case. See, from this one, if you see this one, this is about the different energy levels of an hydrogen atom for the ground state, that is minus 13.6 electron volt. First energy state, second energy state, as move on, keep on moving, the electron energy volt is keep on increases over here. See, from this one, see, in this case, what they are asking, what is that frequency? According to this one, see, first thing is, if see, let me tell you here, for the first transaction I just mentioned here, transition here is 2 to 6. From 2 to 6, first transition. Second transition is about 6 to 2. And see, already you know this one. Whenever the electrons are excited, it will be moving from the lower energy state to the higher energy state. But it won't be in higher energy state for the long time. Again, it will come back to the lower energy state with the release of some energy. Now, I just mentioned here, whenever it's moving from, see here, this one, in this case, whenever it's moving from higher energies to the lower energy state. So what happened here is it release an energy. That energy here is, I just mentioned here, E is equal to energy of photon, E is equal to H into nu. See, if energy is maximum, so the frequency also maximum here. E is proportional to nu, and the nu value already you know this one, nu is equal to C divided by lambda. See, in this case, if frequency is maximum, so the energy also maximum here. If frequency is minimum, so energy also minimum over here. Now, in this case, for the third transition here is, see here, transitions from 2 to 1, and the fourth transition is from 1 to 2. So here in this case, 1 to 2, in this case, it won't be the answer because the transition is from 1 to 2. Whenever the energy will release, if the transition is from higher energy state to the lower energy state. So these two won't be there, whether this one or this one will be the answer in this case. Now, in this case, I just mentioned here, for this one, the transitions between these two, see, 6 to 2 I just mentioned here, 6 to 2 transition, this release of energy here is 0.368 to 3.40. The difference you can see this one in this case. Now, next one is 2 to 1, 2 to 1 from here. This case, this green color you can observe here, 2 to 1, that transition is in between in this one, minus 3.4 to minus 13.6. This energy difference is maximum, so the frequency also maximum in this case. Now, this is about the Lyman series, and this and all, this is about the Balmer series. This is a visible range of light, and you can understand here, wavelengths keep on increases in this case. This is about Lyman series. So the answer in this case here is this one. Hope you can understand here. Problem, this is quite interesting, but you have to remember some of the values. Let me tell you the previous one problem also, the energy levels of different states also you have to remember. See, similar this one. In this case, let me tell you how many revolution does an electron complete in 1 second, time period of 1 second in the first orbit of an hydrogen atom. So hydrogen atom they have given, hydrogen atom means here in this case atomic number is that also 1, and the first orbit n also 1 here. In this case, what they are asking here is how many revolution in this case, this is about the frequency. See, the first problem itself I have shown this one, the time period. The time period is directly proportional to n cube by z square, but a number of revolution in this case, that will become a frequency here. So I just mentioned here inverse of time. See, I just mentioned in this case frequency f is equal to 1 by t of n. That one I just mentioned here in this case, m z square e power 4 and whole divided by remaining thing I just write on here 4 epsilon naught square and h cube and n cube here. See, from this one, similar here is mainly proportional to what are the things here is z squared divided by n cube. So according to this one I just mentioned here, but in this case frequency I just mentioned here. So this one, what are the things are vary over here is z square and n cube only varying here. Now remaining these two, all these combined together, what you are going to have the value here is, so this one you need to remember here, 6.62 into 10 power
15 into, see here, z square divided by what you are having here is n cube. Now substitute all the values here. 6.62 into 10 power 15 into z, that is about atomic number here is 1 square, and the number of transition here is first orbit. So here is n equal to 1. So what you are going to have, the answer here is 6.62 into 10 power 15 hertz. This is about the frequency in this case. Okay, next question here is, so this question appear like big, but little easy only. Just concentrate here. Yeah, hydrogen like an atom. Atomic number they have given. Atomic number here is that is in a higher excited state of quantum number n. See, this is an excited state. Atomic number here is S, Z. So then this excited atom can make a transition from first excited state by emitting a photon, by emitting a photon of energy. See, first excited state, it emits an energy they have given. Alternatively, the atom for the same excited state can make a transition from second excited state by emitting photon. See, first excited state emits a photon, energy value here is 27.2, and the second excited state they have given the energy value here is 10.2. See, from this one, the electron value of n and z are given by. See, what they have given here is from what is that atomic number, and what is the number of from which state which has been moving, that is similar to 10.2 in this case, or even 27.2. See, they have mentioned here n number. What is the number that we have to find, and z value we have to find out in this case. Already we know this one. This is the formula here I just mentioned here. See, this one del E is equal to, this one will be similar like 1 by lambda, same concept here, but here we are going to mention this energy value here, that is about 13.6 Z square, that one into 1 by N1 square minus 1 divided by N2 square. See, in this case, for the first one I just mentioned here, for the first one, that is about a 27.2 electron volt, that one will be equal to 13.6 into Z square. So here the transition is from 1 by 2 square minus, this is about the first transition, 1 by n square. This is about the first equation here. Now this one I just mentioned here. This is the first equation, and the second equation again I just mentioned here. That one what they are given here is 10.2 into 13.6 Z square. This is 13.6 Z square divided by 1 minus 3 square. This is the next state, second transition, and divided by 1 by n square. See, from this one, what we are going to find out here is, we are going to find out n value and z value. See, from this one I just mentioned here, from equation 1 divided by equation 2. Now I just mentioned here, in this case, so that one here is 27.2 divided by 10.2. That one I just make it at approximation as 27. This one make it approximation as 10. So what you are getting here is 2.7. 2.7 you just round up it, that will be around 3 here. Now this one I just mentioned here, 13.6 Z square into, so this one here is 1 by 4 minus 1 divided by n square. This is first equation, whole divided by, again the same, 13.6 Z square into 1 divided by 9 minus 1 by n square. Now in this one, these two are common, will be cancelled here. This one already I told, approximately 3. And this one multiply over here, that is 1 by 9 minus 1 by n square. Now this one here is 1 by 4 minus 1 by n square. Now multiply this one, cross multiply it, arrange it here, and what you are going to have, the n value here is, from this one n is equal to, approximately you just find out here, n will be around 5 to 6 will be there. Now I just consider as 6 in this case. Now if you consider this one in all the cases, see here, In this case, you just go through all the answers over here, so you can understand here. In this case, whether it may be a 6 or even a 8, not 8, so maybe a 6 or 4 like that will be there. According to this, you just plan. Now, I just mentioned here n equal to 6 approximately. Now, substitute n equal to 6 value in any one of the equation. N of equal to 6 here is to the equation 1. Now, you just substitute here. So here is first equation is similar one. Any one equation you just consider 27.2 into 13.6 and z square, that one will be equal to 1 divided by 2 square minus 1 divided by 6 square. Now you just simplify this one. This is for approximately 2 time over here. From this, if you simplify here, see similar like this one, this is 1 by 4 minus 1 by 36. From here, z will be equal to approximately 3 will be the answer. So from this case, you just solve this one, get the answer. The answer in this case here is this one. The next problem here is, let V1 be the frequency of the series limit, series limit of Lyman series. Series limit in this case, what you mean by series limit in this case here is, that is a shortest possible wavelength, which means it is having a wavelength is shortest means energy is maximum. According to this formula, hope you know about this one. According to energy of photon here, now I just mentioned here, E is equal to h nu. Now in this one, as the nu here is c divided by lambda, so hc divided by lambda, I just mentioned here hc divided by lambda here. Now in this case, if wavelength is increases, energy is decreases. Now in this case, shortest possible wavelength, that means if wavelength is shortest, in this case energy of photon will be increases. I just mentioned here double mark so that you can understand over here. Now what you mean by series limit, I just mentioned here series limit in this case, which is having a shortest wavelength. Now I just mentioned here series limit means short wavelength lambda, and energy here is more energy is more. Okay, that is maximum photon energy. I just mentioned as maximum photon energy. Next one, first line series. See here what they have mentioned here in this case. Now in this case, first line series. Now here, first line series of Lyman series. What you mean that here is first line, I just mentioned here. First line in this case, which is having a largest possible wavelength. See here, large wavelength lambda here. Wavelength is largest, which means what about energy? Wavelength is largest means the energy will be decreased, the shortest wavelength. Now we have seen already the frequency formula nu is equal to this one 1 by t. Hope you remember this one. From here, c into 1 by n square minus 1 divided by m square here. Now frequency here is 1 by lambda is equal to formula will come. Hope you remember this one. N is r z square into 1 by c, this one z square into 1 by n1 square by 1 by n2 square. Like that the formula will come. From this one, instead of c, from use this relation from here, see from this one you can understand here nu is proportional to 1 by lambda. Now substitute the value, but here c, this is constant, not a velocity. Hope you remember this one. This is constant here. See, instead of z square and all, for that I have mentioned as c constant value. For series limit, for the first case I just mentioned here, series limit here is n is equal to 1 and m here is infinity. Now infinity, m is equal to infinity means in this case you can mention here. So I just mentioned here 1 divided by 1 square minus 1 divided by infinity. Infinity value here is 0. So what you are going to have here is, in this case I just mentioned here, nu 1 will be equal to c. Now for the second case I just mentioned here, for the second case, that is first line series of Lyman series. First line here is, in this case, n is equal to 1 and m is equal to 2. Now you just substitute this value here. From this one, n is equal to 1. I just mentioned here 1 square minus m is equal to 2 square here. Now you just simplify this one. What you are going to have here is nu 2 is equal to 3c divided by 4. Now this one, you are having the constant term c will be there. Hope you remember this one. Next one, third one. Third one is about a Balmer series. Balmer series. Again, this one also series limit. So from this case, next series n equal to 2 and m is equal to infinity. Now in this case, Again, I just mentioned here C into n is equal to 2 square here and m is equal to infinity. From this one, you just substitute nu 3 is equal to C divided by 4. See, from all these four answers will be there. Now you just substitute here nu 1 equal to nu 2 equal to, from this concept, nu 1 equal to, first case I just take here C minus for the first option A. Yeah, I just take this one. New one value here is C minus new 2 value here is 3C divided by 4. So what you are going to have here is 4C minus 3C divided by 4 here is C by 4. So answer in this case, first one. Okay, the next problem here is an alpha nucleus, that is alpha particle nucleus of an kinetic energy bombards an heavy nuclear target of charge they have given Z into E. This is charge with atomic number, charge of the nucleus they have given. See, hope you remember this one in the first presentation of the first problem. I have mentioned this diagram. Hope you remember this one. This is about the alpha particle which is bombarded to this one. The distance between the particles to the closest approach to this one. Hope you remember the first diagram. I have mentioned in that one, that formula also I have mentioned. You just go through. I just give you the link on this section. You just go through on this one. According to this, here is the kinetic energy. Alpha particle, whenever it's moving here, is it's having a kinetic energy. That one will be equal to the targeted atom. That will be equal to that potential energy. Whenever see this kinetic energy which is greater than this potential energy, so that what is going to happen, that's minimum energy. Hope you remember about the work function. That's minimum energy is enough to remove the electrons. Similar like this energy is see, from this one, this energy is more than enough to remove the electron. Whenever it's bombarded to this one, this energy, the kinetic energy should be maximum, so that it remove the electrons. So scattering is going to happen. In this case, what they are asking here is the distance closest approach. So now this one I just mentioned here. In this case, kinetic energy here is I just mentioned as 1 by 2 m v square here. Now see the distance, that is about how much about the radius, that is mainly proportional to. See this one, I have mentioned this one in the first problem. You just go through on here. 2e into, that is 2 charge, that one will be equal to, because that is alpha particle. Hope you remember 2he4, alpha particle here is 2, so that I just mentioned here 2e, and divided by distance here is r naught. Similar, I just mentioned like a similar like a Coulomb's law. You just go through the first problem. See, from this one, r naught will be equal to r naught. I just take it on this side. Remaining thing I just keep it over here. See, from this one, 2, see 2 into 2e here is 4e square z into k divided by m into v square. See, from this one, r naught is proportional to 1 divided by 1. So answer in this case here is this one. The next problem here is in Rutherford alpha scattering experiment with their gold foil of 8,100 scintillations per minute. Scintillation is the simple, is like a process where it emits a flash of light. As per this one per minute, 8,100 flashes will be produced over here. That means that much amount of the particles will be scattered in Rutherford alpha particle scattering experiment and observed at an angle of 60 degree. Now at a 60 degree of angle, the previous one we can see this one, at a 60 degree of angle, 8,100 flashes was being observed per minute. The number of scintillations per minute at 120 degree. See, 60 degree they have given the splashes. At 120 degree, what is the splash? See this one in Rutherford experiment. You have to remember this formula. See here, alpha particle scattering at an angle of angle is given by n is equal to q and t z square e power 4 divided by 8 by epsilon naught r square e square, and c here sine power 4 theta by 2. You remember this one. And in this case, this is about q is about alpha particles which is striking on this one, that will produce 8,100 of scintillations over here. And this one n is about a number of atoms per unit volume, and r is about, see here, r is about distance of the screen from the foil, and T is about the thickness, Z is about the atomic number, and what are the things they have given here is about the angle of scattering over here, and even a kinetic energy of the particle. Now from this one you can understand here N is C. From this one N is proportional to T, N is proportional to Z square, N is inversely proportional to R square, N is inversely proportional to E square, and even N is inversely proportional to sine power 4 theta by 2. All the data has been given from this one. See here, from here what we are going to find out here is only about that angle. See, only angle has been going to change according to the, see this one, this is for a 60-degree angle. What about 120-degree angle of number of scintillations? That one only we are going to find. See, from this one what I'm going to mention here is, from this one n is proportional to 1 divided by sine power 4 theta by 2. See, from this one n1 equal to the same concept, that is about 60 degree here, n2 here is 120 degree here. So now from this one n1 divided by n2 I just mentioned here, n1 here is, see this one I just mentioned as 1 divided by sine power of 4, 60 divided by 2, and the next one is about see here, that is 1 divided by sine power 4, that is 120 divided by 2. Now I just substitute and I will take it over here. See what you are going to have here is sine power 4 60 by 2, and the next one here is sine power 4 30 by 2. Now sorry, that is 60 by 2, that is 60 by 2, I'm sorry, this one 120 by 2 here is 60 here, and 60 by 2 here is 30. Now you just substitute the values here. See, from this one already they have given the values over here. See, here is this one here is 8100 divided by n2 here, and then you just substitute the values here. Sine power 4 of sine 60 is 1 by 2 here. Now sine 60 degree, and root 3 by 2 sine power 4 of 30 degree. Now you just mention here, simplify this one, and what you are going to have that answer here is 8100 divided by 9. From this one you are going to have 900 answer in this. Okay, the next problem here is an alpha particle of energy they have given, that is about the kinetic energy here is 5 million electron volt, is scattered through 180 degree by a fixed uranium nucleus. Now this one, see here, one is about alpha particle. So alpha particle means I just mentioned here, alpha particle in this case I just mentioned here 2E4, and next one is about uranium. Uranium I just mentioned here 92 uranium U235, right? For in case of an isotopes, this one. Now here is 235 or 234 here, isotopes it may vary, and the distance of the closest approach is in the order of, now closest approach in this case they are asking about R value. Now according to this one we have seen this one. See here, kinetic energy here is K is equal to this one, I just mentioned here 1 by 4 pi epsilon naught q1 q2 divided by r. Now this one 1 by 4 pi epsilon naught, already you know this value, 9 into 10 to the power 9 into one charge here is, that is about helium, so I just mentioned here 2e here. Another one is about uranium. Uranium here is z into e. Hope you remember this one, q2 I just mentioned as z into e, so that one here is 92. Uranium atomic number here is 92 here, 92 into E, and divided by R, and energy already they have given, that is 5 million electron volt, means 5 into 10 power 6 million you can mention, or even mega also you can mention here. From this one R is equal to 9 into 10 to the power 9, and to 92 into 2 into 92 I just mentioned here. 92 you just approximate for the calculation purpose. See here, you are not going to use the calculator, so I just make it in an approximation. And this one E square here is charge square, and divided by, and what they have given the value here is 5 into 10 to the power 6. Now you just cancel here 10 to the power 6, and this one, this will become 3 here. Now here is 9 into 10 to the power 3, and 90 into 180 over here, and multiply with 1.6 into 1.6 into 10 to the power e square, right? Now this one here is No, I mentioned here 1.6 here is 1.5. 1.5 I just mentioned as 3 by 2 into 3 by 2 into 10 to the power minus 19. Minus 19 square will be there. Now minus 19 square I just mentioned here, and whole divided by 5. Now see from this one, see from here what I'm going to mention here is you just cancel it over here. Now this one you just cancel over here. See from this one and multiply over here. Simplify this. What you are going to have the answer here is 5.3 into 10 to the power minus 12 centimeter, not a meter. So meter in this case 10 power minus 15 will come. They are mentioned in centimeter. So you just convert this one. So what you are getting, that answer in this case here is 10 to the power 12 order. This is quite interesting. You just go through on this problem. See here, the transition from the state of 4 to 3 in hydrogen like atom. See, this is not hydrogen. This is hydrogen like an atom results in ultraviolet region. See, in this case, let me tell you in this case. See, what they have mentioned here is 433. See, transition from fourth orbit to the third orbit. What they have mentioned here is result in ultraviolet region. See in this case, this one Balmer series you can understand here, all are visible region of color. See below the Balmer region, all are Lyman series, that comes under ultraviolet. See here, this is violet, this side here is ultraviolet. And after the Balmer series like a Paschen, Brackett and P1 series, all three are infrared. See this side is red, this is infrared, this side is violet, this is ultraviolet. Now what they have given here is 4 to 3 transition like an hydrogen, that is ultraviolet. See, do you have anything? You just see here 4 to, see there are only one thing is there, 4 to 3 is not there, 4 to 1 only it's going, that is a Lyman series, so that you can have a ultraviolet region. But the 4 to 3 what they have given here is, you just go through on this one, this is 4 here. See, this is in this case 4 to 3. You can see this is not a Lyman series. This is a Paschen series. Paschen series you are having infrared. So they are mentioned as ultraviolet, but this is actually infrared. So this is not a this is not a ultraviolet region. This is infrared region. So infrared region will be obtained from transition from, what are the transition will be obtained here? See, you just see 2 to 1. See here, from 2 to 1 what you are having here is, this is ultraviolet region, but they are asking about infrared. Next one is 3 to 2. You just see here, this is 3 to 2. 3 to 2, this is visible region. See, you can see this one. One is about 2 to 1. Next one is 3 to 2. This is visible region. Next one is 4 to 2. See here, 4 to 2. What is this there? See, you just see, this is 4. 4 to 2 here is again, this is visible region. Then come to here, 5 to 4. See, 5 to 4, you just see here, 5 to 4. Yeah, this one 5 to 4 you are having, that is also a infrared region. So infrared region, what are the things will come in infrared region means, you can mention this one. See here, 4 to 3 will be there, or even a 5 to 3 will be there, and even 6 to 3, 7 to 3, 8 to 3, or infinity to the 3, you are getting this one. This is infrared. Or even bracket series, you just see here 5 to 4 and 6 to 4, 7 to 4, all are comes under infrared. If they are mentioned here 5 to 4, 6 to 4, 7 to 4, or even this one 4 to 3, 5 to 3, like that means you can get the answer here. See this one similar like this one here is, you can see two, this one here is 5 to, see sorry, 6 to 5, or even a 7 to 5, or infinity to 5. All these three cases are infrared. So that answer in this case here is this one. The next problem here is hydrogen 1H1, deuterium 1H2, and singly ionized, one time only ionized singly, that is helium 2He4, twice that is doubly ionized lithium. See, that is 3 Li8 double plus, all have one electron around the nucleus. See, on the outermost orbit, one electron in the nucleus, and consider an electron transition from 2 to 1. Now, see, in all the cases, hydrogen, deuterium, and even helium, lithium, in all the cases, transition from 2 to 1, it's going to happen. Then wavelength is emitted from the radiations. For hydrogen, lambda 1, helium is lambda 2, and this one deuterium is lambda 2, helium is lambda 3, and lithium is lambda 4. So the what is that values according to this one? See from this one, already you know this one I just mentioned here. Lambda value here is this one I just mentioned here. In this case 1 divided by lambda, that one will be equal to, hope you know about this one, r z square into 1 by n1 square minus 1 by n2 square. Now in this case see here 1 by 1 square n1 square minus 1 divided by n2 square. Now in this case I just substitute here from the transitions from 2 to 1. See in this case, in all the case, for the first one I just mentioned here 1 by lambda 1. In this case I just mentioned as 1 by lambda 1 is equal to r into atomic number for hydrogen here is 1 square, and 1 divided by n1 square is in all the cases this is common, 1 by 1 square minus 1 by 2 square. So from this one what I'm going to mention here is this one r into 1 by 1 square is 1 by 1 minus 1 by 4. So what you are going to have here is 4 minus 1, 3, 3 divided by 4, that is 3r divided by 4. Right. Next one. See from this one again 1 by lambda 2. See similar here 1 by lambda 2, again I just mentioned here r2 is equal to, again here also this is hydrogen atom. So the transition is from here, that is 1 by 1 square. The same, all the transitions are same over here. Now again I just mentioned in case of lambda 2 also the same. So from here what you are going to have, say this one even the same, 3 lambda 1 and lambda 2 in both the cases I just mentioned here 3 r by 4. And next one is about lambda 3, 1 by lambda 3 here. So this one I just mentioned here r into lambda 3 means this is helium, right? Helium means 2He4, that is 2 here, and the same transition 1 by 1 square minus 1 by 2 square. So this one here is 3 by 4, 3 by 4 into, again see here 3 by 4 into r, again your 2 square here is 4. So what you are going to have here is 3r. Now last one I just mentioned here similar like this 1 by lambda 4, I just mentioned here what you are going to have here is r into 3 square. Similar this one here is 3 by 4, same transition. See from this one what you are going to have here is, I just mentioned here this is about uh, this one here is 9 into r, again 3 by 4. Right, here is, so you just mentioned here 4r, or even in this case you can mention like this, or even you can mention as a 4r 3 by 4. Now in all the cases I just mentioned the answer over here in this case. So I just mentioned as 1 by lambda 1, and here is 1 by lambda 2, that one will be equal to, here is lambda 3 I just mentioned as here as a um, 1 by 9 lambda 4, that one will be equal to 1 by lambda 3, here is 4 lambda 3. That all in this case, see here from this one all the case what you are going to have here is see I just mentioned here this is all these things that is common here, that is 3 by 4r. You just take a 3 by 4r in this case. So this is a common here. So 3 by 4r, say from this one what you are going to have here is I just mentioned here. So the final answer will be equal to, just inverse it, lambda 1 and lambda 2, and here is 4 lambda 3 and 9 lambda 4. So answer in this case here is this one. Here is energy is required for the electron excited in lithium from the first to the third orbit. Now what you mean by excitation? Let me tell you in this case. See here, here whenever the electron from for this one I just mentioned, for a electron in the ground state, whenever it receives an energy, so that the electrons get excited, it will be moving from the ground state to the excited state. So that's what they have given. So how much energy is required for this electron which is moving from ground state to the next immediate excited state? For this one, see here how you can measure the energy of electron here is, I just mentioned here this one del E. Del E is equal to this one, you know this formula, 13.6 Z square. That one will be equal to 1 divided by N1 square minus 1 divided by N2 square. Now from this one see here, this one I just mentioned here 13.6, and the lithium atomic number here is, hope you know about this one, is that here is 3 square, 3 square into, from where to where it's moving from first to third orbit. So that I just mentioned here n1 equal to 1 by n1 square minus 1 by n2 square, here is 3 square. Now substitute the value, then from here 13.6 into 9 into This one you just simplify here. 1 minus 1 by 9, that is 8 divided by 9. Now 9 and 9 will be cancelled here. 13.6 into 8 here is 108.8 electron volt in this case. Answer here is 108.8 electron volt. Next question here is, what is the ratio of Bohr magneton to the nuclear magneton? So what is the formula for Bohr magneton and nuclear magneton? Once you know about this one, this will be little easy here. First one I just mentioned here, mention as Bohr magneton. So Bohr magneton formula here is, that one will be equal to, so EH by this one, EH by 4 pi into this one here is mass of electron. Now next one again, same I just mentioned, that is a nuclear magneton. So nuclear magneton here is nuclear magneton. So you have to remember these two formula. Here also the same, but here EH divided by 4 pi into nuclear, in this case that is about mass of proton. So what they are asking here is the ratio of Bohr magneton to the nuclear magneton. So common term EH by 4 pi, EH by 4 pi will be cancelled here. So what you are going to have here is, see, 1 divided by ME and 1 divided by M into P, that is mass of electron and mass of proton. So what you are going to have here is MP divided by ME. So answer in this case, remember this formula, directly they will ask such type of question. Problem. Out of the following, which one is not possible? Remember here, which one is not possible for a photon to be emitted by a hydrogen atom according to Bohr's atom model? See, one thing you can understand here, according to Bohr's atom model, see the energy of the electron which is at the ground state and first, second, third excited state. These are all the excited state. That one they have given the energy, that is a minus 13.6, minus 3.4, minus zero point 0.5, and like that, next one like this will be there. For this case, let me tell you in this case how you can find out with the help of this one. See, let me show you the formula which can be used to find the energy in the different states here is, for example, for the nth state, En is equal to, that one here is minus 13.6 electron volt divided by n square, depends on, this is about number of orbit here. For this one, first one I just mentioned here, E1 for the first state here is, I just mentioned here, E1 is equal to, n is equal to 1, so what you are going to have 13.6 electron volt. Similarly, E2 is equal to, E2 here is minus 13.6 divided by 2 square here is 4. So minus 13.6 divided by 4, what you are having here is 3.4 electron volt. Now next one is E3. E3 here is the same one, 13.6 divided by 9 here. So 13.6 divided by 9, what you are having here is 1.5 electron volt. Similarly, minus 1.5 electron volt. Next one, E4. E4 I just mentioned here, minus 13.6 divided by 4 means 4 square, that is 16 here. So 13.56, 13.6 divided by 16 here is minus 0.85 electron volt. So in all the transition, suppose if the transition is in between, I just mentioned here, what they are given, photon emitted. See here, transitions that going to happen. So that one we have seen. Previous one, from higher orbit to the lower orbit, I just mentioned. For example, if I take third orbit means it will go to the second or first orbit. So that I just mentioned here. Third orbit here is, what you are getting, that value minus 1.5, minus of first orbit here is minus of minus 3.4. So what you are going to have here, that is 1.9 electron volt. Do you have 1.9 electron volt? Yeah, you are having 1.9 electron volt. So here what they ask, not possible. So one has been confirmed. Similarly, second one I just see here. For example, if I take a E4, E4 means E4 to it will go to E3 or E2. Now I just mentioned here E3. So E4 value here is minus 0.85 electron volt, minus E3 here is minus of 1.5. So what you are going to have again here is 0.6 0.65 electron volt. Do we have at 0.65? Yeah, the first option will be there. So that also possibilities are there. Next one we'll see about E4. E4 to E4 to E2 is there, E1 is there. I just mentioned like a E1 to find out the answer. So E4 to E1 here is minus 0.85, minus of E1 value here is minus into minus plus, that is minus 13.6. What you are going to have here is 12.75. So 12.75 electron volt also is there. So next option 12.75, that also options will be there. So in all the cases, what options will not possible here is, in this case 11.1. You won't get this possibility. So answer in this case here is 11.1. Here. A hydrogen atom initially in the ground level absorbs a photon which excited into fourth level. See, from the ground state to the fourth level it has been reached, that is n equal to 4 level. The wavelength of photon is, now what they are asking here is wavelength of photon, that is third excited state. See, n equal to 1 means that is ground state. First excited state n equal to 2. Second excited state, this is n equal to 3. Here is n equal to 3 means second excited state, n equal to 4 means third excited state. In this one, how much energy has been required? See, for this one, I just mentioned here, energy changes here is del E is equal to this one, E1 minus E2. That one will be equal to energy of photon here is h nu, and nu equal to c by lambda, so hc divided by lambda. Now what they are asking here is lambda value. So lambda is equal to hc divided by delta E. That is about changing energy level from the first state, ground state, to the third excited state. So here H Planck constant value here is 6.624. This one point here, 6.624 into 10 power minus 34, and velocity of light 3 into 10 to the power 8 whole divided by, now from the ground state value here is 13.67 minus 13.67, that is a third excited state, divided by n equal to 4 square, that is 16. Now if you cancel here, what you are having here is 0.9. See, from this one I just mentioned here 6.6, I just mentioned this one only, 6.6 into 10 power, this one here is minus 26 into 3. So this one I just cancel here, and divided by 13.67 minus zero point 0.9, what you are getting here is 0.9 here. So this answer is in joule. So you have to convert this one in electron volt, that is 6.6 into 10 power minus 26, and you just cancel here, divided by 0.3. Now already you know this one, that is 1 electron volt is equal to 1.6 into 10 power minus 19 joule. See, from this one, 1 joule is equal to 1 divided by 1.6 into 10 power minus 19 electron volt. So instead of 1 joule, what I am going to mention here is, here I just mentioned this one, in this case, into, instead of 1 joule I just mentioned as 1 divided by 1.6 into 10 power minus 19, this one electron volt. From this you just cancel here, and this one you just cancel it, and divided by 0.3. So what you are getting here is approximately 97 into 10 power minus 9, sorry, this is minus 9 meters. Now not 99, this is minus 9 here, or else. So what you are going to have here is answer in this case 970 angstrom. So answer in this case 970. So for next question here is the speed of the electron in a nitrogen atom in the n equal to 3 level, where n is equal to third orbital level. What is the speed of the electron? The first one we have seen the velocity of the electron. We have given the formula. Now this one I just going to mention about derived formula here. The velocity of electron v is equal to c divided by, there we have mentioned like a 13.6 electron volt, that has been derived into 137 into z divided by n. Yeah, Here Z is nothing but atomic number of hydrogen atom, that is 1, and where n equal to 3, already they have mentioned here. 3 is velocity of light, so 3 into 10 to the power 8 meter per second divided by 137 into, see here, Z value is 1 and divided by 3, this 3 will be cancelled here, that is 10 to the power 8. Now this one 10 to the power 8 divided by 137, you just simplify and derive this one. So what you are going to have here is 7.3 into 10 to the power 5 meter per second. That is about the velocity of the electron at the third orbit. So answer in this case here is this one. Of this presentation. Next I am going to discuss about uh, problems on nuclei. This will both, it will be covered from NEET as well as EAMCET problem. It will be discussed in the upcoming presentation as a two-part. You just go through on this one. If you are having any doubt, you just mention here and put your doubts on the comment section so that I can respond to that. Next one, this one will be covered. In addition, first year portions also I am trying to cover unit and measurements. That will be the next presentation. That one also will be there in addition, side by side. In another track, I will cover that one also.